Look, there is a problem at the screen, and we are going to solve it. And here is the problem: a uniform rod. Look, let me show you which one is the rod. In fact, this is the rod of mass m. It's suspended by light inextensible ropes of same length from the ceiling. The rope length, these are the ropes. Rope length and rod length are same, and is in a position of stable equilibrium. That if I take the side view of this picture, this is something like that. Yeah. And a small bead of mass m can move along the rod without friction. Well, fine. At the initial moment of the time, the taut ropes are pulled back by an angle alpha from the vertical. Oh, this is the case. Okay. And there is a bead I would like to show you like this. And so that the rod and the attachment points of the ropes to the ceilings lie in a vertical plane. Of course they will lie, and the bead is in the middle of the rod. Yeah, fine. Find the acceleration of the bead immediately after the rods are released. Okay, so rod is released, and and okay, fine. And alpha is practically constant immediately after the rods are released. From here it is released, and I need to find the acceleration of the bead. Okay, this is the problem at hand, and we have to solve it. So how can we do it? uh, let's see how can we do it. I think during the motion, the ropes, rod, and the section of ceiling, well, between the points of attachment of the ropes is a parallelogram. I'm focusing myself when each of these things has been pulled back to an angle alpha with the vertical, and they are going to get released now. At this moment they must be forming a kind of parallelogram, or I guess something else. Parallelogram is the right word. And after they have been released, and the rod will remain parallel to its initial position. That means the rod will perform a translational motion. If I consider only rod, they will perform the translational motion. Okay, so I need to write down the translational kinetic energy of the rod at some point of time. So let us consider that our system, after a certain time interval, very small time interval, just after the system was released from rest, so we are going to consider the motion of the system just after the ropes were released. Just after, that means after a very small time interval. And let me show you a picture before doing anything else. Yeah, here is the picture showing all those things. So that in this small time interval, this rod has ends of the rod has performed a displacement delta s. You would like to call it ds, it's fine with me. And the bead has come down to a vertical displacement by delta h. So this length is delta h, and here is an angle alpha between the initial position of the rope and the vertical, and their corresponding perpendiculars are horizontal. Of course not in this direction, but horizontal. And the length that is perpendicular to the because the time interval is very small, so it should perform a displacement perpendicular to this length. So this length is delta s and this length is delta h, and horizontal and perpendicular, this angle should be equal to alpha, so that I can write here delta h is simply delta s sine alpha. And that means at this moment, if I consider the velocity of how can I relate? Yeah, I can relate the displacement of bead delta h with velocity of the bead. At this moment, if the velocity of the bead is v and velocity of the rod, I'm relating it with displacement of the rod. So velocity of the rod by u, I can write at this moment at an angle alpha, that v equals u sine alpha. Okay, so this is a kinematic constraint. I found one. Now what? Now I would like to find the potential energy, because under the action of vertically directed gravity and the reaction of the rod, that is not changing the potential energy at all, because there is no friction, the bead will perform a vertical displacement delta h. It has already performed a vertical displacement delta h in vertically downward direction, so that the potential energy of the whole system has been decreased by an amount delta u, and this should be written as m plus m g delta h. This is the decrease in potential energy, so it will cause an increase in kinetic energy of the system. And I would like to write it as a law of conservation of energy, that m plus m g delta h, that is decrease in potential energy, equal to increase in kinetic energy of the system, that is half mv square plus half mu square. Capital M is the mass of the rod and small m is the mass of the bead. So I would like to write it in this direction, and then I have to find out the acceleration of the bead, and bead is acted upon by the gravity and the force of reaction exerted by rod on the bead. So I don't know what can be it. If it was only under it, I wonder if the bead would have moved under the action of gravity only, then it would have the acceleration g, but this is not the case. So I'm going to use v square equals u square sine square alpha and write it here. And finally I will be getting something like that: v square equals 2g delta h m plus m divided by m upon sine square alpha plus m. This is the v square, and we assume that the time interval delta t is so small that the acceleration of the rod and the bead on this interval can be considered constant. And then I would like to write something, the equation like v square equals 2a delta h, that directly comes from v square equals u square plus 2s. And after comparing these two equations, I can get the acceleration of the bead like g m plus m divided by a small m plus m upon sine square alpha. And so this is the acceleration of the g. We did all these things because this time interval delta t was very small, and we were considering all those things at the moment. And if delta t is considerable, that means it is not very so small, then all these results are wrong, and I would not be able to solve this problem. So I solved it for a moment, at that particular moment, and I got the acceleration. I didn't find any other way to do it, so I did it in this way. Thank you very much for watching.